Hello, everyone, and good morning, good afternoon, good evening to everybody where you are. I see that two of our audience has joined from India. So let me introduce Ajinkya, who is the speaker of today, and I will just read about his qualifications from the lab website. So he works as a PhD student in the Boundary Layer and Turbulent Research Group in the University of California, Irvine, within the group of Dr. Tirtha Banerjee. And he did his bachelor's from IIT Kanpur, where he worked primarily in the field of CFD. And then he did his master's in the aerospace engineering of UC San Diego, and where he worked on the analyzing oceanographic field data to explore the mechanisms of cross-shore transfer in the inner shelf of the coast of Point Loma. Now, in his PhD, he is basically working on the Grassland fires, and he's analyzing the field experiment data, and probably he is doing also some CFD, which he will present soon. So Ajinkya, now the floor is yours. So please carry on.
Okay, thanks so much, Chandan. So I'm just going to go ahead and share my screen. I hope. Thanks so much for the introduction, Chandan. And thank you for being here, everyone. And thanks for having me here as well. So as Chandan mentioned, we shall be looking at some PIV data that was collected during a burn experiment, a small-scale burn experiment for a grassland fire burn experiment in a small grassland region. And it was conducted by Scott Goodrick from the US Forest Service, the Southern Research Station. My name is Ajinkya Desai, and I'm from UC Irvine. And we were actually given this data by Scott Goodrick from the US Forest Service. But before we go into that, I would actually like to, sorry, let me just change my pointer over here. I'd like to motivate this a little bit. So, I mean, you may already know this, you might from just reading the news or surfing the internet, but within the United States, if I can motivate why we should study fire behavior with the help of some statistics, if you look at the year-to-date statistics by a notable fire management center, it says that in the year 2021 up to 26 November, there have been 52,000 fires in the United States alone, and 6 million acres of land have been burned. If you look at a 10-year statistic, year-to-date statistic, you would see that acres burnt have been of the order of millions, and the fires have been consistently of the order of 50,000s. Right, so it pretty much fire management is pretty much an urgent issue. Also, on the day after Thanksgiving, that is 26 November, 26 November this year, firefighters had quite a bit of a job to do. They had to contain 7 fires across the country, across the US, and they also had to tackle 4 active fires. They're still active. They have not been put out, and they have already burned 90,000 acres. So this just puts into context the urgency with which we need to be able to understand fire behavior. Also, if you watch a certain TV show or a documentary actually on Netflix called Fire Chasers, new firefighting trainees are asked to ingrain in themselves the motto, know what your fire is doing at all times. Quite understandably so, right? Given the necessity of fire management training. So from a fluid mechanics point of view, we want to be able to understand how fire-atmosphere interaction, how turbulence engendered from fire-atmosphere interaction governs the spread of the fire and the dispersion of smoke, which is important in the context of visibility for those who are trying to manage the fire, and also air quality, and which in turn affects human health for those who are living in a fire-prone region. We also want to be able to investigate the validity of the existing analytical and computational models. So we look at some experimental data in order to do that. Before, again, we go into the current the research, I'd like to first just throw throw back to a time when, well, fire research itself began in the US decades ago in 1940s. But if I could pull out a fire growth model that is quite recent, I would pull out this one, the Rogers model. It's a kinematic model. And the crux of this model is that it actually relies on the wave propagation model for fire growth. So what that means is every point on the fire perimeter at a time t acts as an ignition point for a local fire that emanates from that ignition point. And so that the fire perimeter at time t plus delta t would be given by the locus of these small local fires. So that's the wave propagation model. It's a kinematic model, has been used very frequently. But if you were to look at an experimental, a recent experiment conducted by Finney et al., actually this was a laboratory experiment, they observed that the fire front has these regions of has counter-rotating vortices, which cause the formation of regions of downwash and upwash. They're alternating regions. Furthermore, they also advect hot gases from the flaming region onto the unburnt fuel. There are certain CFD analyses as well. One of them is this research by Canfield. What you're seeing over here are streamlines that indicate, and a fire front. And streamlines coming in from the upwind side indicate the wind driving the fire in the heading direction. But you're also seeing some streamlines being diverted towards a flanking region, and that is causing the fire to spread in the flanking region as well. So we have an analytical model, you have experimental, and you have some CFD analysis over here. What we have is PIV data. So we're looking at experimental data. But this is not a large scale analysis. This is a relatively small scale analysis. So then what, after going through all of that, all of those slides we just mentioned, the scale at which fires are affecting us, how would such data collected at a relatively small scale be helpful? So turbulence measurement itself requires high temporal resolution, and being able to observe coherent structures requires substantial spatial coverage. Most of the research that we have so far have studied detailed flame structures, which are useful in their own right. Some examples include buffing in pool fires. You have premixed flames, entrainment in premixed flames, useful in their own right. But turbulence measurements have been limited to point and space observations. So it's not so much PIV data available on spreading fires. Only quite recently has PIV been employed to understand fire spread in vegetative fuels. In this analysis, we have high frequency PIV data, which covers a relatively sizable area in space, but also it has a high temporal resolution. So it satisfies both these criteria that have been mentioned above, which is why they're useful in tracking velocity vectors within the site as the flame structure evolves, as the fire spreads away from the ignition point, which gives us some new insights, some different insights into the environment that around a fire arising from, with focus on turbulence arising from fire-atmosphere interaction. I have here a video. Thankfully it does play. So essentially, we have a fuel bed over here that's comprised of hand-drawn pine needles. They've been spread by hand, so there might be some heterogeneity in the fuel. It's a relatively small domain of 2.34 by 2.34 meters squared. The fire was ignited, the fuel bed was ignited near the center of the domain, and the flame was allowed to spread, the fire was allowed to spread in the absence of any ambient wind forcing. The day was chosen in such a way that there weren't any strong ambient wind gusts, which is why the rate of spread was relatively low, 0.2 to 0.3 meters per minute. It's quite low. Measurements were taken for the longitudinal horizontal velocity and the transverse horizontal velocity. So we just have two-dimensional measurements, but the vertical velocity was computed by setting the divergence of the velocity field to 0 and then integrating to a height equal to the grid size of this two-dimensional domain. That's how we got the vertical velocity. We have approximately 7.5 minutes of data, so not an extremely long time series, but still good enough. And a sampling frequency, a quite high sampling frequency of 30 Hertz for this data. I'll be introducing the data to you via flow visuals. So we'll be looking at some color contours. Then we look at some coherent structures that characterize a turbulent flow. And then I'll wrap it up by looking at only the important terms of the turbulent kinetic energy budget equation. Flow visual. So if you look at what you're looking at over here are color contours of the horizontal velocity magnitude. You're looking at different snapshots in time. If you look at the fire front in the initial stages of the fire, you see that the fire perimeter forms a closed loop, and it spreads more or less radially away from the ignition point, this red spot that you're seeing over here. But there comes a time around 110 seconds, which is a quarter of the way through. The fire perimeter responds to instabilities in the flow field and starts forming fire pockets. So it's no longer a closed loop. And these fire pockets are centered at points which have very, very low horizontal velocity. And so we call them fixed points. They are visible much more clearly at a later point over here, 247.5 seconds. We'll be basing some of our analysis around this snapshot as well. So you see these two fixed points. Now, if you come back again to 110 seconds, once the fire has formed these pockets, the fire front spreads by virtue of relocation of these fire pockets from the ignition point. And that, to a certain extent, validates the wave propagation model, which I had discussed in the context of the literature review, that every point on the fire perimeter acts as an ignition point. And the local fires that germinate from that ignition point give us the location of the new fire front if you were to take the locus of the new pockets of fire. If you look at color contours of the surface temperature before the formation of the fixed points, you'll be able to see that the fire core is made up of naturally a very high temperature. But if you overlay vectors of the horizontal velocity, you see that colder air from the outside is entrained into the warmer fire core, and that is expected, right? Because the warmer fire core is going to generate a region of low pressure and draw in air from the ambience, from the surroundings. That structure gets carried over when you see smaller fire pockets being formed after the formation of fire pockets. So you see the same structure, you see entrainment from all directions. Moreover, if you were to look at the color contours of the vertical velocity, you see that the fire perimeter, again, naturally is made up of a region of updraft. The yellow over here is positive vertical velocity. So it's made up of a region of updraft. But it is circumscribed by a region of downdraft. And that is again expected because this is what would be in line with continuity. So we have a fire perimeter, which is a region of updraft surrounded by a region of downdraft, which is the dark blue. Again, the same structure gets carried over when you see these fixed points themselves being flaming regions and surrounded on the outside by flaming regions being regions of updraft and then surrounded by regions of downdraft. If you were to look at the total velocity, you'll probably see a fuller picture. So these blue arrows are regions of downdraft on the outside of the fire per se, and the fire perimeter itself is made up of a region of updraft. But because there's entrainment from the outside, the flame would be tilted inward, as would be expected if there would be entrainment from the outer side. What you're looking at over here, moving on to now coherent structures, we just looked at the flow visuals. What you're looking at over here are cross-correlation contours. So for the streamwise velocity, the u velocity, that is longitudinal velocity, the transverse velocity, that is the v velocity, and for the vertical velocity, i.e. the w velocity. Essentially, these are cross correlations of a certain velocity component with the same velocity component at the ignition point. So if you look at the U velocity cross correlations, what you're going to see over here are y directionally elongated structures for the U velocity. And for the V velocity, you're seeing x directionally elongated structures for the V velocity. What that means is that entrainment is a bulk response to the presence of the flame in the initial stages of the fire. So there's a fire flame, and then it immediately starts to entrain air from the ambient region, and that's a bulk and immediate response. If you look at the vertical velocity component, vertical velocity component cross correlations, you see that in the initial stages of the fire, there seems to be a preferred direction for the spread of the fire. That might be because of heterogeneity in the fuel bed, but then owing to perhaps a local shift in the wind, there is another change in the direction of the fire, and then the fire starts to spread in more or less in the radial direction, radially away from the ignition point is what I mean. On the outside, you'll see these negatively correlated cross-correlation contours. Negatively correlated with the ignition point would mean that the velocity here is downward, which means these are regions of downdraft, because the ignition point would being a region of updraft would have a positive velocity. So this also attests to that structure that we were seeing in the flow visuals, that the fire perimeter is circumscribed by a region of downdraft on the outside. Now, moving on to some more interesting features, interesting coherent structures. So if we take a snapshot in time, and if you plot the horizontal vorticity vectors after computing them, of course, just the horizontal vorticity vectors, so within a plane, if you use a right-hand thumb rule, then you will see that the fire perimeter is made up of counter-rotating vortices, or they are in the vicinity of the fire. It also, if you will see them even if you traverse the fire. So you're seeing counter-rotating vortices if you were to use the right-hand thumb rule, right? Taking this further, if you were to plot a vortex line that correspond to these vorticity vectors, you see that these vortex lines originate outside, way outside the fire perimeter, spiral their way inward toward the fire perimeter, where they get denser at the location of the fire perimeter, and then as they move their way inward into the fire core, they get sparser again. So if you were to take a streamwise transect and plot the horizontal vorticity magnitude, so the magnitude of these vorticity vectors, you see that the horizontal vorticity magnitude is increased at the location of the fire front. That is where these vortex lines get denser. That is where the vorticity magnitude is stronger. And the circulation structures that correspond to this increased vorticity would look like so. And this would mean that the horizontal velocity induced by these circulation structures are pushing hot gases outward, away from the ignition point. So there'd be hot gases being pushed outward in this direction and in this direction. And that is what we are suggesting is causing the fire to spread, because it's pushing hot gases from the flame towards the unburned fuel. So counter-rotating vortices are being the key mechanism over here for pushing hot gases outward and initiating and causing fire spread. Now, actually, let me go back to the previous slide. Okay, so if you focus on this picture over here, if you just focus on the vorticity vectors, they are in the XY plane. We still have to add the vertical vorticity vector, so the omega z component. These vortices, since the axes are aligned in the XY plane, these vortices are vertical vortices, right? Now, if you were to add an omega z component, let's say that omega z component is positive over here, right? It's positive upward. That would mean that the net vorticity would be pointing in this direction, in the upward direction, which means this eddy, which is currently vertical, is going to get tilted so that its axis is pointing in the upward direction. If you were to look at this eddy over here, and let's say the omega z component is negative, then by a similar logic, this eddy or this vortex is going to be tilted downward, so that you have a downward tilted eddy, you have an upward tilted eddy. So if you can imagine that, you'll be able to see that these vortex lines get twisted upward. The vortex lines that we were looking at on the previous slide get twisted upward and get twisted downward. And that happens alternately in the upward and downward direction, depending on the strength of the omega z component. So you're getting, if you were to imagine a vortex tube between consecutive vortex lines, these vortex tubes are getting kinked as they're spiraling inward towards the fire perimeter. Perhaps you see that better by looking at the helicity color contours. So helicity is a dot product, the inner product between the velocity and the vorticity. So if we know, if you remember from that picture, the three-dimensional picture, the fire perimeter is made up of a region of updraft, so U pointing upward. If your net vorticity is pointing upward, which means if the eddy is tilted in the upward direction, that means the angle between them would be acute and you'd get a positive dot product, which corresponds to these red regions over here. If it is, if the eddies are tilted downward, then the angle between these two may become negative. I'm not saying it does for sure, but when it does become negative, what you're seeing over there are, when it does become obtuse, the angle between them becomes obtuse, so that the dot product, inner product, becomes negative. That corresponds to these blue regions over here. So if you were to traverse the fire perimeter, you'll be seeing regions of updraft and downdraft, not updraft and downdraft, regions where the vortex lines are kinked upward or they're twisted downward, upward and twisted downward. There's always going to be a region of updraft in terms of velocity, but the vortex tubes or these eddies are going to either precess upward in this red region or downward in the blue region. So this is a kind of a visual representation or maybe more a mathematical representation of this of these kinked vortex tubes. This itself, the picture itself, is quite hand-drawn. So we're seeing kinking of vortex tubes. Now this is at time t equal to 100 seconds. Let's see what happens when these fixed points are formed. So it seems like there's a question in the chat box. What does the arrow in red color represent? Is it fire or hot gas? Arrow in red color. So to go back to the previous.
In the figure there where you presented the vortex lines.
Oh, okay. Oh, these arrows?
I think so. Chotilal, you can unmute yourself and ask the question.
Yeah, hi. In figure B, this red arrows, what is showing? So is it the fire direction, or you are talking about gas?
Those are vorticity vectors. So it's the same vorticity vectors that you're seeing in this image. You're just looking at a top view now.
Yeah, and
yeah.
So the figure below B, where you are showing this vorticity versus distance. From the point, the arrow is showing that gas will be going away from the center, and again, like from the other side, around 1.5, arrow is showing that it will go away from the center. So basically, the hot gas is trying to escape the center, and it is spreading outward. So yes. How does this particular arrow will be correlated to the figure B? So I could not get these two correlation points.
Oh, good. Okay. Yeah, thank you. So these two arrows are induced velocities. These arrows that you're seeing over here, these red arrows in figure B, these are vorticity vectors. So if you were to use the right-hand thumb rule, you would be seeing eddies of this kind. So if an eddy that is going out of the plane and inward like that. So basically you're seeing these eddies because of these are arrows that represent the axis of these circulation structures. And these arrows, blue arrows over here, are representing the induced velocity of these circulation structures. Does that make sense? So I'm going from the arrow to the circulation structure to these induced velocities. That's the sequence.
Yeah.
Good. Thank you. Yeah, thank you for the question.
I also have a question in the next slide where you showed the topology of the kinked vortex tube.
Yeah.
So when you basically when the fire front is spreading, and you showed previously that experimentally we have seen some fire pockets, right? Within this vortex tube. So what would be the mathematical topology of those pockets here? Is it too complicated to idealize, or?
Yeah, so this is before the fire pockets are formed. This is at 100 seconds. This is when the fire front is nice and closed and still spreading radially away. Yeah.
But yeah, so when the fire pockets are formed, what could be the topology of this system, of the main vortex?
Yeah. I have not alluded to, so I have not alluded to the kinking when the fixed points are formed, but I have a similar analysis once the fixed points are formed for the horizontal vorticity. That might perhaps answer the question that you have.
Sure. Okay.
So yeah. So if you take another snapshot when the fixed points are formed, and then you focus your attention around these fixed points, and again, like if you were to plot the vortex lines that correspond to these horizontal vorticity vectors, so again, these red arrows are the same as these blue arrows, and this red arrows in E are same as the blue arrows in D. And you plot the corresponding vortex lines, you will see that these vortex lines emerge from one fixed point, spiral outward, and then spiral inward towards another fixed point. So there is some kind of an interaction between these two fire pockets through these eddies that correspond to these vortex lines. Moreover, the vorticity dynamics of these two fixed points is isolated from the rest of the vorticity field by virtue of this line that you see over here, which is a closed vortex line. So it's this exchange, I would suggest, would be exchange, as it were, would be isolated or secluded from the rest of the flow field. Now, I have not added the vertical vorticity vector over here, but I think my guess would be that it would resemble what you're seeing with the closed fire, because again, these fire pockets are similar to that closed fire. It's just that it's a small fire pocket. And then you have the big fire, which is made up of the locus of all of these fire pockets. But one small fire pocket itself, the dynamics would look, the picture would look just like it would for that closed fire pre-instability. Except over here, you also have this other fixed point, and there's some kind of an interaction between these two fire pockets as well. So there will be kinking, there'll probably be some kinking, but then it is not just surrounding one fixed point. Maybe there's something going out of here, going around the other fixed point as well. So there's some interaction over there.
I expect that the vortex tube will be broken, right? I mean, it would no more be a continuous vortex tube at some point. Do you expect?
Yeah, I would expect that too. So I think there's, if you look over here, I think pretty much it looks like there's some kind of a there's some kind of a bifurcation.
Yeah, so I was also interested. Did you do any dynamical characterization of these fixed points? I mean, in terms of its stability?
Yeah, okay, Chandan, you're asking some really good questions. Actually, that's something that we are projected to do sometime in the future. We would have to do a stability analysis, thinking of these as as attractors in a system.
Yeah, exactly. This should be like, since again you told that it's a completely turbulent situation, I would be like really interested to look at the basins of attractions of this.
Yeah. We are thinking of doing that. It's actually Tirtha's idea. We are thinking of doing some bifurcation analysis in the future too. Right now, we are far from it. We are very far from it. So we have to literally start with thinking about which equation to use, because
I think you might have to come up with a dynamical closed form equations for that. And like, do you also have idea to like fit a dynamical model from the experimental data that you get, which resembles the dynamics in terms of the fixed points and so on? Is that a plan? I'm just curious.
So actually in the slides to come, we're actually going to look at some budgets So we're going to look at some kinetic energy budget equations. So we're going to try to fit this data into some mathematical expressions and see what happens. If you're thinking of a stability analysis, then I think an equation that we could use would be perhaps the Orr-Sommerfeld equation or the Rayleigh equation. But then again, that does not factor in the presence of the flame. If you were to include account for the presence of the flame, there are actually some mathematical models that actually document this in a paper. There are several equations. It's just mathematically so complicated to solve because you have to account for mass conservation of solid phase, you have to account for mass conservation in the liquid phase, then there is chemistry, then there's thermodynamics as well. So there are several equations that you have to take into account when you want to, when you mathematically want to quantify what's going on over here. It's very complex, and that's why doing it in a CFD setting also requires a large amount of simplifications, so a lot of simplifying assumptions.
I expect that the models will have a few empirical constants at least, which will be fitted from the experiments. If you want to come up with a dynamical system model, but I'm not sure whether it's done in the literature. It's very complicated. I can understand. Yeah. Please go ahead. Yeah.
Sure. Thank you. So essentially I want to close the discussion on the coherent structures by just indicating that there is some kind of an interaction between these two fixed points. And the reason I emphasize that is because we see something similar happening when we look at the TKE budget, the turbulent kinetic energy budget equations. We're going to focus on the fixed points over here in that regard. So if you were to do a very standard Reynolds decomposition as we would do in turbulence on the velocity components, this should actually be UI, not just U, that I being the initial notation, where the average quantities are not absolute means, they're moving means, so they're 1 minute moving averages. And if you subtract those from the velocity, from that corresponding velocity component, you will get the velocity fluctuations, which are the primed quantities. And so that is what you can compute from the data that we have. And then you can use that to compute the turbulent transport term of the TKE budget equation. This term represents turbulent transport if E is a TKE. And this represents the shear production term. This represents the buoyancy production term. Now, the thing is, for buoyancy production term, which includes temperature theta over here is temperature and temperature fluctuations, we don't have data for temperature fluctuations of the air. We have data for surface temperature. So at this point of time, we are not able to calculate the buoyancy production terms. Shear production is useful in this case, but I'm going to, for now, skip the discussion on shear production because the most interesting thing is most interesting things are happening with the turbulent transport term. So focusing again at these two fixed points formed at 247.5 seconds. If you look at the turbulent transport term, we're looking again at 1 minute moving means for these two fixed points. You see that decreasing trends at one fixed point are accompanied by increasing trends at the other, and vice versa. You have increasing trends at fixed point one accompanied by decreasing trends at the other. That seems to suggest that there is some kind of energy exchange that is happening between these two fixed points via the turbulent transport term. Now, this is not unique just to that set of fixed points. If you look at fixed points that are formed at other instances in time, and if you plot the turbulent transport term, you'll see peaks in one corresponding to troughs in the other signal, and decreasing trends in one signal complemented by increasing trends at the other signal. And you would see that for other sets of fixed points as well at other instances of time, increasing trends accompanied by decreasing trends. So that seems to suggest again that there is some kind of an interaction between adjacent fixed points based on via the turbulent transport term. So the vorticity structures pointed towards some kind of an interaction. The turbulent transport seems to be quantifying that interaction via an energy exchange. So if I were to summarize this in 3 points from this really busy picture that I have over here, it's a hand-drawn picture. But if I were to sequentially summarize this, the flame causes the flame creates a low pressure region within the fire core, which entrains air from the ambient region, okay? Then on the outside of the fire front, you have a region of downdraft. The fire front, the fire perimeter itself is made up of a region of updraft. So that's point number 1, actually. Then you have these circulation structures over here traversing the fire perimeter, which push hot gases outward. Those hot gases are actually being pushed from the flame towards the unburned fuel, and that hot gas which is going towards the unburned fuel is igniting the unburned fuel. So that is what is causing the fire to spread outward. So the circulation structures are the key mechanism for the fire spread. Third, when these fixed points are formed, there is some kind of an interaction between these fire pockets. You see that from the vortex lines. You also see that from the turbulent transport term. Why is this important? So in the field, actually, there have been observations where fire lines that are close enough but still far away get attracted towards each other. So fire lines in the field get attracted towards each other somehow, possibly because of this turbulent through the mechanism of this turbulent transport term, or some kind of a vortex interaction between those two fires, or between those two fire pockets. In the future, we are looking, maybe in the near future, we would like to look at some 3-dimensional PIV data in order to investigate fire whirls. Fire whirls are formed when these vertical eddies get tilted because of the updraft. A strong updraft tilts these vertical eddies. Basically, the vorticity vectors of these are in the horizontal direction until they get tilted, so that you have a strong omega z component, which means there's going to be a strong circulation in the horizontal plane. And that circulation causes the fire flame to form these whirls. We got a taste of this from looking at those kinked vortex tubes, but then again, that's just this is essentially 2-dimensional analysis, and we just have the vertical velocity component at one point, at one plane, so at a point in at points within a plane. We don't have a vertical resolution for the vertical velocity. We would have to do some 3-dimensional data collection for that. So we are looking forward to doing that sometime in the future. Actually, the postdoc that's coming into the lab might do something like this. And then, and Chandan, as you pointed out, we are hoping to investigate the cause of the instability mathematically, somehow quantify. So if I were to go back to the previous slide over here, you see these fixed points over here, and they have a fire pocket that centers these fixed points. But you see that the fire pockets are adjacent to each other, but they are not, but they're still distinct from each other. But then at a later point of time, they coalesce with each other as well. So you see these two have coalesced with each other. So we don't just have formation of fixed points from a disintegration of the fire front. We also have them coalescing. So that's going from one in bifurcation language, maybe going from one limit cycle to another limit cycle, or one mode to another mode. So we would like to investigate that sometime in the future, and we would have to really start from scratch when it comes to that. So that's all I have for now. Thank you so much.
Thanks, Ajinkya, for this very interesting and nice talk. So I have a few questions, but before that, I would let the floor open to the audience. So please unmute yourselves and ask if you have any questions to Ajinkya. Shuman, do you want to ask anything? I think you would be interested in this.
Yeah, I was listening to the talk. It's an interesting topic. Like, unfortunately, I've sort of moved away from macro scale CFDs to more like molecular and micro scale CFDs. But yeah, combustion is something that I do work on. If you could, I'm sorry, I joined a bit late. So I didn't hear the first few slides. I think so. What platform are you using for doing the simulations? Is it like a in-house standalone code, or are
This
you
is
using
an
something that?
experimental data. Yeah, Ajinkya, please, can you please explain?
Oh,
Yeah,
it's
no problem.
entirely PIV data, so it's no modeling on the side, right?
Yeah, no, this is just there's no CFD analysis in this, actually, no simulations. We're just doing data analysis of some experimentally collected data.
That's fine. That's nice.
Yeah.
Thanks. Cool.
Yeah,
Nice, man. It's really nice.
Thank you.
Yeah, but I want to like ask a follow-up question here. So how difficult do you think to model it in CFD, and what could be the challenges?
Yeah, extremely difficult, because because the equations that describe fire flow are extremely complex. Well, rather than complex, I'd like to say that there are many equations. So there are mass conservation equations for the solid state, for the fluid phase, ash, smoke particles, all of that. Then you also have the Navier-Stokes equations for the flow. You also have thermal effects, right? And you have chemistry going on. So one state being converted to another, there's combustion. So there's a laundry list of equations that need to be accounted for. So that makes it quite difficult. And then you have to do some simplifying assumptions. You have to employ some simplifying assumptions. And some studies in the past have tried to do CFD simulations, and it is extremely taxing when it comes to, so I don't quite remember the exact domain sizes that they use, but I think for a relatively small scale simulation of the order of a few meters to a few meters time a few meters, it took I think more than a week. And it was not even giving an entirely accurate estimate of what was going on because of all the simplifying assumptions involved. So it is extremely taxing when it comes to CFD research.
Yeah, but do you think that can we simplify the like model or the governing equation to capture the essential dynamics by considering just a multi-phase combustion model? I mean, if I really ignore the particle physics here, or so the multi-phase combustion models does something similar.
Okay.
I mean, the thing I was curious, the picture of CFD simulation that you showed in your motivation, what kind of framework they used? Like, do you have any clue?
Yeah. So that was using
Can you
something
go
called,
back to the picture? Can I see?
Yeah, definitely. So I don't entirely recall, but I remember that this was done using I think a finite volume solver called FireTech or HighGrad. It was one of those. I don't quite recall what their simplifying assumptions were, but this is wind-driven fire in one direction, and I think.
And I expect it to be some sort of large AD simulations, seeing the pictures.
Yeah. It is LES.
So what is the like order of Reynolds number here? Is there any governing Reynolds number for the physics?
I'm not sure if there's some kind of a critical Reynolds number. The Reynolds number in our case is actually quite low. So if you were to look at the turbulent Reynolds number in our PIV data, it is something, it's like it's of the order of a few thousands. I think with their data, I think it's an order or a couple of orders higher. I don't recall, but it's turbulent flow, so it's quite high Reynolds number. And considering again that actually that kind of answers your question, is like if we have a really high Reynolds number, then you have to really be mindful about stability and accuracy. So it's going to be quite taxing for computational resources if you're trying to simulate high Reynolds number flow.
Right.
Yeah.
Yeah.
Yeah, I was just going through this paper. They do use FireTech and Ajinkya.
Yeah.
I'll just add to that. I mean, so most of the research that goes on in combustion, I'm like not a hardcore combustion guy. I sort of lie in the mid domains. Combustion people just solely are concentrated on combustion. I mean, they're not that much bothered about Reynolds number per se, because they want more of the fuel to be burned, and for that they want the fuel to be as low velocity as possible. So the inertial forces are not so dominant for people who are in hardcore combustion field. And for the equations that you were mentioning, and yeah, I mean, there are things like people use, I think it's called COMSOL, and also ANSYS, they use something called a chemkin, which involves like the equations jumps in 32 multiples, I guess. You can involve 32 reactions or 64 reactions or 128 reactions, however you want. But I guess the accuracy of that depends on people are coming up with new propellants or fuels that they want to burn. And I'm sure replicating something like a cellulose or a wood that actually exists in the nature, that would involve you at least involving 100 to 200 equations. But
yeah, there's heterogeneity to be taken into account as well. Yeah, sparseness, and the sparseness of the for instance, if you're doing a canopy flow, then you have to take into account variations due to the density of the foliage, how sparse the canopy is.
Yeah, pulling that off with the domain size that you had, yeah, even a week will be like really pushing it. So that'll definitely be something, I guess. If you have access to the National Lab supercomputers or something, you can just put simulation to run and just forget about it for a month or something. And
oh yeah. I think those simulations, if you're looking at canopy fires, for instance, so this is a grassland fire, and this is quite a tiny domain. It's very tiny. It's just a few meters per few meters. But if you're looking at canopy fires, they're of the order of several meters, several meters. I mean, the resolution is actually several meters. So that is going to take a really long time for sure. Yeah.
So I was actually curious that in this problem, apart from Reynolds number, which non-dimensional number is the most important for to change the physics in terms of, the topology of the vortex tubes, or let's say the fixed points behavior. So because I'm not aware, so what's your control parameter? Let's say if you really want to see different transition to the physics, so what would govern that? Which non-dimensional parameter would govern that?
Yeah, that's a good question. Not quite sure. I'd say I think isn't no, I don't think the Froude numbers got anything to do with it.
I mean, again, I'll just answer it from a perspective of just the fire and the combustion. I mean, from fluid mechanics perspective, definitely the Reynolds and stuff, but just for a combustion and heat transfer stand view, there's something called a Peclet number, which is that's just for the transport of the heat.
Okay.
There are also things like Knudsen number, but Knudsen number actually goes into very small scale combustion stuff, where you compare the mean free path with the length scales of the problem. But again, this is since this is a large scale problem, I guess.
I mean, the thing is, here you just set the fire experimentally and observe the temporal and spatial evolution of the fire front, right?
Yeah.
So, and if you want to do another experiment, you just basically change the initial conditions to it, right? So set another fire at another point, but you don't have control over the environmental characteristics. So my point was that do you do an air field characterization before setting the fire? What is the turbulent field there, and what is the spatiotemporal behavior of the wind at that condition? So does it matter to the physics?
Yes, very much. So I don't know, I'm not sure if anyone sets up takes any eddy covariance measurements, but local meteorological stations do take wind measurements at 10-meter heights. And those measurements can be used to decide whether to perform an experiment of this kind or not. So for instance, over here, if you're looking if you're trying to get a fire that is not wind driven, then you're going to choose a date and time that is where the wind measurements at the local weather stations indicate that it's calm, so that the wind velocity measurements are going to be very low. If you are looking for a prescribed fire, so this is not a wind driven fire so much, but there are head fires which are driven by the wind. So where the fire front is being pushed forward by the wind, actually. So this is simulating a head fire. The wind is pushing the fire front forward. There are also backing fires where the fire front is advancing against the direction of the wind. So that happens in prescribed fire conditions. So if they're trying to conduct a prescribed fire where they're trying to eradicate certain amounts of fuel before a natural fire hits, or if you're just trying to do some data collection for backing fires or head fires, taking into account the wind is very important. So you have to study some of the local synoptic wind conditions, the weather conditions in a region before you try to conduct an experiment of that kind.
Yeah, because it's as you said, even if I like characterize my environment to be calm, or let's say it's not wind driven, even that, as you mentioned before, like the reproducibility of the same physics, it's quite difficult, right?
Very difficult, yes.
So because it's spatio-temporal in that sense. So but my question here, that the topology that you are identifying, how robust that is. Let's say the local flow behaviors changes, but this kinked vortex tubes or the fixed points in the fire pockets, so are they robust? I mean, did they do multiple experiments to find out some sort of uncertainty, or how do they, or it's just a single field experiment?
No, this is just a single field experiment. And alluding, like, in answer to the robustness aspect, yeah, there is a lot of uncertainty, to be very honest, because they have not taken any wind measurements during the fire. So you could always have some local shifts in the wind, which is just not being measured over here. Secondly, these are hand-drawn pine needles. These are hand-drawn pine needles. So there's definitely going to be even some heterogeneity in the fuel bed. Yeah.
So basically what we are looking at in the temporal evolution or the spatial evolution, it's basically transient, right? And which can change for every experiment.
Yes, it's very unsteady. Yeah.
Yeah.
So that is why we have to do, look at, the aim is to look at some coherent structures, some structures that persist in the flow, rather than trying to quantify every aspect of it. Yeah.
Yeah, so basically the other thing that I already asked, it would be really interesting to see like whether some sort of lower order dynamical system model exists. I mean, even maybe fitted from the experimental data and with lots of simplicity, but if we really have a maybe ignoring the speciality of the problem, just have a temporal dynamical system model which could give us the fixed points and then the stability of them. That's really interesting.
That would definitely be very interesting. Yeah, certainly. And when it comes to I think quantifying certain coefficients, I think that is also an area of active research. So for instance, looking at the Reynolds stress term, so the U prime V prime term or U prime W prime term, I don't know if I discussed that anywhere. Yeah, but if you just look at the flux term, U prime, UI prime, UJ prime, that shows up as a Reynolds stress in the Navier-Stokes equations, right? And that is where the problem of turbulence closure is faced, right? And you want to be able to close it. You want to be able to simplify that. And so people want to use eddy diffusivity models. So a lot of research is actually going into how do we quantify those Reynolds stress terms by using an eddy diffusivity, when actually in a lot of environmental system, it fails.
Yeah.
So I think a lot of experimental data is going into investigating things like that as well. Investigating, for instance, an eddy diffusivity coefficient. How do we quantify that so that we can simplify some of those terms when it comes to modeling them?
Yeah.
Yeah.
So I wanted to also ask, in this data analysis from the PIV data,
Yeah.
so what algorithm did you use to find out the fixed points? So what is your approach?
Oh no, there was no algorithm. It was just from looking at those snapshots. It was literally from looking just at the snapshots. So, I mean, you have a grid, right? And if you just plot the horizontal velocity magnitude, it's just visually noticing that these are regions of low.
Do you search for some measure that which becomes zero or something, like the local velocity, or you just by eye estimation do it? That's
Oh,
very
I just seriously, but just by eye estimation, because this is a very I'm actually very familiar with the time series, because having looked at different snapshots so many times, I can just visit a certain snapshot in time and then try to find a point in the array that shows very low horizontal velocity magnitude. Incidentally, those points also correspond to very strong updrafts, because
yeah.
those are the points where the fire flame is actually residing in that instance of time. Yeah. So no algorithm to answer your question. It's quite visual and quite crude in that sense, actually.
Okay.
Yeah.
Yeah. So that's all I thought I should ask you. And
Sure.
if nobody has any more questions, we can close the session. And thanks a lot for accepting our invitation to give a talk.
No
It
problem.
was really interesting. So I'm looking forward to read your works when published in future.
Sure.
On space, especially I'm more interested in the dynamical system approach, because my work also is at the intersection of nonlinear dynamics and fluid mechanics. So I try to see if the system is nonlinear, what happens to the fixed points. That's very important.
Yeah, and I don't know if you would like to. I guess this is also Tirtho's call and your call as well. But maybe we should talk to Tirtho about this and see if we could collaborate on this aspect.
Yes, sure.
Yeah.
I mean, let me know. I'll be really interested, but it depends on Tirthoda. So so we can talk about it. But let me know. Even if we don't collaborate, I'm always free to discuss with. So you can just ping me and we can discuss. It's very interesting. Thanks a lot.
Thank you.
Yeah. So have a good night for you. It's being late.
Yes.
And I'm just starting the day.
Okay.
So
we'll have a good rest of the day.
Okay.
Sure. Being in different parts of the world.
Yeah. Because they're brought together by technology, I guess.
Yeah, that's a good thing. Yeah. And since the talk is recorded and it will be archived, so many people will observe it in future. Okay. So probably, I think you have no problem in uploading this talk in our YouTube channel, right?
No, I have no problem with that at all.
Okay. Thanks a lot for that.
Yes, sure. Thank you so much.
Yeah. Bye.
Yep.
Bye.
Have a good day. Bye-bye.
Yeah, bye,
Bye, Suman.